Okay, hello again. Alright, so we're moving on to the next chapter even. Because I read a little bit about this and it's exciting, so I want to do it. Forgive me if I cough or whatever. So, got fresh bread baking in the oven, so we got 35 minutes to work. In the previous tutorials, we learned quite a lot about lighting in OpenGL. We learned about Phong shading, materials, lighting maps, and different types of light casters. In this tutorial, we're going to combine all the previously obtained knowledge by creating a fully lit scene with 6 active light sources. We're going to simulate a sun-like light as a directional light source, 4 point lights scattered throughout the scene, and we'll be adding a flashlight as well. To use more than one light source in the scene, we want to encapsulate the lighting calculations into Glsl functions. Yay! This is really cool. And I knew that this was possible, I just didn't put 2 and 2 together. The reason for that is that the code quickly gets nasty when we want to do lighting computations with multiple lights, with each light type requiring different computations. Exactly what I was thinking when we had to change the fragment shader so much. If we were to do all these calculations in the main function only, the code quickly becomes difficult to understand. Okay, so functions in GLSL are just like C functions. We have a function name, we have a return type, and we'd have to declare a prototype at the top of the code file if the function hasn't been declared before the main function yet. We'll create a different function for each of the light types: directional lights, point lights, and spotlights. Perfect. When using multiple lights in a scene, the approach is usually as follows. We have a single color vector that represents the fragment's output color. For each light, the light's contribution color of the fragment is added to the fragment's output color vector. So each light in the scene will calculate its individual impact on the aforementioned fragment and contribute to the final output color. A general structure would look something like this. Out color main, define an output color. Add the directional light's contribution. Some function to calculate directional light. Do the same for all the point lights. 0 to number of point lights. Output plus equals some function to calculate point light. And add other lights as well, like spotlights. Output plus some function to calculate spotlight. Color equals vector for output. The actual code will likely differ per implementation, but the general structure remains the same. We define several functions that calculate the impact per light source and add its resulting color to an output color vector. If, for example, 2 light sources are close to the fragment, their combined contribution would result in a more brightly lit fragment than the fragment being lit by a single light source. Okay, so for directional light, what we want to do is define a function in the fragment shader that calculates the contribution a directional light has on the corresponding fragment. A function that takes a few parameters and returns the calculated directional lighting color. First, we need to set the required variables that we minimally need for a directional light source. We can store the variables in a structure called dirlight and define it as a uniform. The required variables should be familiar from the previous tutorial. Dirlight, uniform dirlight. We can then pass the dirlight uniform to a function with the following prototype. Calculate dirlight, light, vector, normal view, okay. Just like C and C++, if we want to call a function, in this case inside the main function, the function should be defined somewhere before the caller's line number. In this case, we'd prefer to define the functions below the main function, so this requirement doesn't hold. Therefore, we declare the function's prototypes somewhere above the main function, just like we would in C. You can see that the function requires a dirlight struct and 2 other vectors required for its computation. Okay, 4.5 minutes before a cough break down there. If you successfully completed the previous tutorial, then the content of this function should come as no surprise. Calculate directional light. Yes. We basically copied the code from the previous tutorial and used the vectors given as function arguments to calculate the directional light's contribution vector. The resulting ambient, diffuse, and specular contributions are then returned as a single color vector. Oh. Point light. Just like with directional lights, we also want to define a function that calculates the contribution a point light has on a given fragment, including its attenuation, of course, can't forget that. Just like directional lights, we want to define a struct that specifies all the variables required for a point light. Position, constant, linear, quadratic, ambient, diffuse, specular, number of point lights. Oh, a constant, that's cool. As you can see, we used a preprocessor directive Glsl to define the number of point lights we want to have in our scene, preprocessor directive. We then use this nr point lights constant to create an array of point light structs. Oh, point lights. Okay. It's point light structs, but the name is point lights. So arrays in Glsl are just like C arrays and can be created by the use of two square brackets. Right now we have 4 point light structs, named point lights, to fill with data. We could also simply define one large structure instead of different structs per light type that contains all the necessary variables for all the different light types and use that struct for each function and simply ignore the variables we don't need. However, I personally find the current approach more intuitive, and aside from a few extra lines of code, it could save up some memory since not all light types need all variables. The prototype of the point lights function is as follows. Calculate point light, vector, frag, position, view dir. The function takes all the data it needs as its arguments and returns a vector 3 that represents the color contribution that this specific point light has on the fragment. Again, some intelligent copy and pasting results in the following function. Right, everything's there. Ambient, diffuse, and specular with attenuation. That's cool. Abstracting this functionality away in a function like this has the advantage that we can easily calculate the lighting for multiple point lights without the need for nasty duplicated code. In the main function, we simply create a loop that iterates over the point light array that calls calc point light for each point light. Putting it all together. Now that we defined both a function for directional lights and a function for point lights, we can put it all together in the main function. Normal, normalize, phase 1 directional light and calc dir light. Phase 2 for the point lights, calc point light. And then phase 3 spotlight, we'll have to add that. Each light type adds its contribution to the resulting output color until all light sources are processed. The resulting color contains the color impact of all the light sources in the scene combined. If you want, you could also implement a spotlight and add its effect to the output color as well. We leave the calc spotlight function as an exercise for the reader. Oh, that's cool. Setting the uniforms for the directional... Ouch! Why am I cramping up there? Okay. Setting the uniforms for the directional light struct shouldn't be too unfamiliar, but you might be wondering how we could set the uniform values of the point lights since the point light uniform is now an array of point light structs. This isn't something we've discussed before. Luckily, it is not too complicated. To set the uniform of an array of structs works just like setting the uniforms of a single struct, although this time we also have to define the appropriate index when retrieving the uniform's location. Oh, okay. Here we index the first point light struct in the point lights array and retrieve the location of its constant variable. This does mean, unfortunately, that we have to manually set all the uniforms for each of the 4 point lights, which leads up to 28 uniform calls for the point lights alone, which is a bit tedious. You could try to abstract a bit away from this by defining a point light class that sets the uniforms for you, but in the end you'd still have to set all the lights' uniform values this way. Let's not forget that we also need to define a position vector for each of the point lights, so let's spread them up a bit around the scene. We'll define another glm vec3 array that contains the point lights' positions. Boom, boom, boom. Then index the corresponding point light struct from the point lights array and set its position attribute as one of the positions we just defined. Then index the corresponding point light struct from the point lights array and set its position attribute. Also be sure to now draw 4 light cubes instead of just 1. Simply create a different model matrix for each of the light objects, just like we did with the containers. If you'd also use a flashlight, the result of all the combined lights looks something like this. As you can see, there appears to be some form of a global light, like a sun, somewhere in the sky. We have 4 lights scattered throughout the scene, and a flashlight is visible from the player's perspective. Looks pretty neat, doesn't it? You can find the full source of the final application here. What about the exercise to do the, yeah. Does it show you? Let's see. Calculate dirt light, calculate point light. Oh, it doesn't do it. Okay. Calculate spotlight is not put in. It's funny. Alright, we made it another 6 minutes to 10.5 minutes. That's not bad. Not bad. Sorry for the coughing. Okay. So there's, yeah. Okay, let's just see what we got here. Ooh, the bread smells good. Okay, so what all are we putting in here? We got some new stuff. What do we got? Not that, not that. Point light positions. That looks new. Positions of the point lights. Did I even close this down? Wow. Okay. Closed it down. Okay, so point light positions. Let's just put it right here. Positions of the point lights. Boom, that worked. Okay. Alright. Sorry about that. Okay, so material. Moving on here. Okay. Oh, look at this. Wow, lots of... And yeah, you're telling me. Okay. Here we set all the uniforms for 5 of the 6 types of lights we have. Yeah. I saw that. So let's just copy everything from lighting shader all the way down. Spotlight. Is that comment? That whole thing's commented out. Oh, they're giving you clues though. That's kind of cool. So we'll copy that and we'll paste it in everything with the camera transformations. Okay, so into here. Create camera transformation. So it's all in here. So right here to there. Paste it in. Okay, and camera model view, everything there. Yeah, this doesn't look like I have to change anything here, so okay. And the vertex shader does not change. So we should have everything right. Let's see what happens here. Whoops, what was all this? Oh, they do a lot of stuff like what? Argument truncation from double to GL float. Where? Where? Argument truncation from double to GL float. So should I... Do I have to do this in each of the... See if that fixes those 2 at least. Yeah. So they just leave off the F, and for some reason that's just truncation. Let's fix them all. Here we go. Alright. Okay. And everything's dark, so I'm guessing that didn't work. So, oh, did we update the fragment shader? Probably not. I don't think we did that. We gotta get that. So let's go into here. Fragment shader. Gotta go look at it. And number of point lights. So that's cool. So, okay, material, dir light. There's the new one, directional light, point light. See, that's great because then you can have those be separate. Okay. Number of point lights. Okay, then you have your stuff there. Dir light, point light. See, this is so perfect for me to just learn from here. Oh, and then you got your function prototypes, and then their functions are defined down here. Dir light, point light. That is so sleek, and then it makes the main function so simple. Okay, great. Great, great, great. Great, babe. Okay, fragment shader updated, and there are lights. There are lights. That's awesome. Oh, but I didn't do the thing for the objects. For where the lights are calculated, but I didn't put in the what do you call it? The transformations for each light and put it in the scene. That would be, let me find that actually. Right here. And we now draw as many light bulbs as we have point lights. See, I didn't do that because it uses the point light positions, and it will. So let's go into the main function down here. Draw containers, cube positions, and then this will be just, yeah. So where's the other light VAO and the drawing and stuff? Did I take it out? I wasn't drawing the lights at all? Well, that's a bit odd, I must say. Ah, there we go. So where are the lights? Oh, cool. There's all 4 of them. I just happened to find them right there. That's cool. There's all 4. You can see them a little better. 1, 2, 3, 4. What's this little guy? Cool. Cool. Very cool. Okay. So that's cool. I realized my error and figured it out. That's cool. Putting it all together. Thank you. Okay, global light, and then, yeah, the image shows all the light sources. Okay, so let's see. They're saying that the, what do you call it? What's putting it all together? We leave the calculate spotlight function as an exercise for the reader. So let's try that. Let's go back to spotlight, where it was before. Point light, directional, multiple lights. Because the spotlight honestly was one of my favorites here, so we're going to have fun here. Fragment shaders source code. I think we're going to use that. Let's leave the other shaders, fragment shader, up there too, because this is obviously going to go inside. So, okay. Now the spotlights. That's where it uses this. That's this whole thing. So the fragment shader with the function, see, the point light, I'm not going to use the directional light because this one's most similar to it, right? Because you've got all this stuff. So, like if we wanted to make a fragment shader function, we're going to go like this: vector 3, spotlight, okay, and then it uses point light, but we're going to go, should we, dir light, yeah, let's just go spotlight light. We'll just do it exactly the same way. And then what do we need? Normal, frag position, and view dir. So for the spotlight, what do we need? We need the position and let's see, point light. Okay, so well, we already have all those things. See, frag position, normal, texture coordinates. Okay, the view position. Okay, the directional, the point lights, and then we're going to need. We're also going to need another uniform. Uniform spotlight, and then we're going to call it spotlight. Or wait. That should be good. And then up here, okay, so for the spotlight, what all do we use? Well, the dir light used direction and used basically the light stuff, so right here. So this is what we're going to need for the spotlight, right there. Position, direction, cutoff, constant, linear. Yeah, the cutoff, and then we also want to put in the, what's the other one? Light.cutoff. And then this isn't the one from the, okay, hold on a second. This isn't the one with the smooth edges. Fragment source code here. So let's outer cutoff. So we need that. Yeah, okay. That's what I was seeing. Okay. All right. And then what am I looking at here? So this will basically go into our function. So we've got the spotlight, we've got the function prototype, or wait, no, we don't have the function prototype. But it's going to be a vector 3, calculate spotlight, and we're going to put it, send in a spotlight, okay? And now keep in mind we have these, so we're going to need the, what, vector 3 normal? Don't we already have that? Yeah, so why do they need that? Let's go look at the point light for a second. Let's go back to the point light. I'm going to figure this out. I'm going to figure it out. Flashlight, spotlight. This one's the point light, right here. Position, yeah. And see, there's the normal, but there's another normal. That, yeah, normalized, normal. Normalized light position frame. So, why does it say that it needs normal? Because it already receives a normal, but does it do another? I'm just trying to think why it has as its input a normal when it already receives a normal through the why? Tell me why. Tell me why. I'm not seeing it. And then the actual function in the thing, vector 3 normal. Oh, is that because, what is it? Oh, no. So, okay, so it's calculating it, then it's throwing it in there. So, what you want to do, yeah, so we'll do that. We'll do the same thing. Sorry, it just took me a second to get that. So it's going to get the normal. Oh, they're giving you a little clue right there too, isn't it? Frag position, view direction. Oh, because it's the same as a point light. It's just got a limited, okay. Oh, well that makes sense. Frag position, vector 3, view dir. Great. Save that. Okay, then we'll come down here and normal, vector 3, frag position 3, view dir. Okay. And now we'll go to the spotlight where it's where everything happens. Copy it in. And this uses the or wait, this isn't it. Undo that. That's not it. Where is it? Outer cutoff right here. It's this one. Why was I thinking it was this one? This was the okay. Alright. I'm just not paying attention. So where does the outer cutoff and all that works in there? Okay, alright. Just gonna copy this. The color that's gonna be return value. So instead of color at the end here, it's just gonna be return because of that last line there. See, return in parentheses that. So this will just be return. Okay. And so everything else looks like it works, right? Ambient equals light.ambient, vector3 texture, material.diffuse. That's going to be from I don't know if this will this work like that or I don't know. Trying to think. Vector3 ambient equals light.ambient times diffuse text chords. That should work. Okay, and then diffuse norm equals normalized normal, but that's actually going to be should that be capital N? Where does this one call that? Light position. Yeah, so it just uses normal there, so let's use the smaller N. Normal, the one that's passed in. It won't have access to the, yeah, I don't think. Okay, so lighter equals normalize light position minus frag, and that's going to be a little f. Okay, difference equals dot norm, which is the calculated one. Great. So that is so weird that we use the same variable inside the function and then inside the actual main, and then you pass it in right there. Yeah, that's, okay, anyways, kind of messed me up. Alright, we're fine now though. Okay, so normalize, wait, where are we at here? Norm, light dir, 0. Diffuse equals light dot diffuse. Okay, times diffuse times vector3 texture material dot diffuse. Do I have to pass in the material, or is that? No, good, perfect. Okay, so that's going to work. Normalize view position minus frag position, that's going to be small. View position, how am I going to get that? Is that going to be accessible? Normalize view. Do we have to pass that in? View dir. Oh, that's in view dir. Okay, so what are we doing? View dir is already passed in, so we don't need that. Just to be on the safe side, let's just do that. Okay, reflector equals light dir, common norm. No, that's the calculated one, so that's fine. View dir, reflector, and that's that variable right there. Material shininess, specular, light specular, spec tech material specular text chords. That's perfect. Light dir, normalize light direction, light cutoff, light outer cutoff, theta, light outer cutoff, density. Okay, diffuse specular, diffuse specular. Okay, intensity is calculated. Attenuation, light position, frag position, that's got to be the small f. Light linear distance, quadratic distance, that's all calculated right there. Ambient, diffuse, specular, boom. Okay, that should work. Of course, that's what we always say. Okay, so let's just try to run that and see what happens. Nope. Errors. Okay. Fragment shell failed to compile with the following errors. 123, redeclaration error. Spotlight. 0, 123. Where's that at? Redeclaration error. Spotlight. So, what's it talking about there? Oh, vector3 spotlight. Spotlight light? No. Oh, this should not be spotlight. It should be called calc spotlight. The heck? The heck you trying to do? Okay, we still have an error. Fin 54. Function does not return match type. One compilation error. Function does not return match type. Oh, right. We're taking off the 1. Is that it? Is that all? Huh? Oh. Did that work? I can't tell if it worked. How do I know? Do you have the spotlight? I don't see the spotlight anywhere. No. Well, it's working, but the spotlight is not working. So it's functional, but not I mean, it's compilable, but it's not working. So, all right, so we're closer. Calculate spotlight. Ambient, diffuse, specular, spotlight. Theta equals. So light dir is up here. Normalize light dot direction. Light cutoff minus light outer cutoff. Theta minus light epsilon 0, 0. Intensity, intensity. Distance. Oh, it would help if I actually uncomment it from here. Okay, alrighty. And we broke it. And it's broken. Great. You know, I think what it is result plus equals but. Thank you for leaving this for as an exercise for because I fudged it all up. Okay. Okay, well, you know what? I gave it a good college try, and apparently I've got it all effed up, so. And I'm not going to edit the video, I'm just going to post it raw on YouTube, so you guys can see my failure and possibly learn from it. Leave your comments in the space below on YouTube. That'd be great. I am going to figure this out and then post a second video, so stay tuned for that. All right, thanks for watching.